So welcome to lecture 9 of MCS 471. We will now properly start the numerical linear algebra part. So last lecture was on linear algebra. Now actually we go more into the analysis. First defining how we can measure the length or the norm of a vector and of a matrix. So we've seen vectors and matrices last time, so we have a whole algebra with it. But actually in this course, when we do numerical analysis, it's actually very important that we can say something about the size. We briefly encountered vector norms when we talked about the size of a polynomial, but here we will generalize this even further to matrices. So before we actually begin investigating numerical algorithms to solve linear systems, it may be worthwhile to look into how hard the problem really is. So there are systems that we cannot hope to solve. Of course, there are the systems for which the determinant is equal to 0. So when the coefficient matrix has a 0 determinant, then we've seen that the LU factorization is not defined. But there's a more general notion of difficulty, and that is and that notion of difficulty is quantified in the condition number. So we will derive the notion of a condition number and also see how we can actually compute it and construct linear systems or construct coefficient matrices that have any condition number that we want. So we can make our problems as easy or as hard as we like. That's very important to know once we test the linear system solvers, the numerical algorithms to solve linear systems. Vector norms. So from calculus, and here it is actually what you probably have seen, from calculus you must have seen the length of a vector by squaring the coordinates and then taking the square root of the sum. Now, we call this the 2 norm. Two other norms that are very popular are the sum of the absolute values or the maximum coordinates, the largest coordinates. So these are the largest coordinate is what is called the infinity norm. The 1 norm, so the sum of the absolute values is the 1 norm. In general, we have a p norm where we take the p power and the p root to get to the norm. Which you pick is of course matters in some sense, but in another sense it doesn't. So in our bounds, when we will often leave off the subscript, so the little p here, we will often leave it off for convenience, just to indicate that the quantities that we derive, that the properties that we derive are independent of which norm we are using. So you can think with the traditional 2 norm, also called the Euclidean norm. But sometimes it's more convenient, instead of taking the square root and the sum of squares, just to take the maximum number in size. When I was on Friday, when I was talking about testing a linear system solver, if you have to solve an upper triangular system, you can actually look at the error on the first coordinate, because with back substitution, that's actually the number that goes through the most operations. Similarly, if you check the accuracy of a lower triangular system solver, it may be worthwhile to look into the last coordinate, the size of the last coordinate, the size of the error there. All right. What are the unit vectors? Well, with the 2 norm, you have the unit circle. So you could say that the unit circle consists of all the endpoints of the vectors of the unit vectors that start at the origin and end at the circle. So the 1 norm, the circles then become a diamond. With the infinity norm, the circle then gets stretched into a square. But you see with this picture here that the norms are actually quite related. If something is big in one norm, it's most likely also going to be big in the other norm. So which norm you choose may matter, but in general, they correlate very, very well. That's what this unit picture here essentially shows. So unit vectors, they will be used to define the norms of matrices. Vectors are special matrices, and a matrix is a table of numbers, so two-dimensional table of numbers. But we can also see a matrix as the definition of a linear map. So if you multiply A times X, where X is a vector, then what you get out of this is another vector. And that's a map that is linear. The sum of two, the images of the sum, is the same as the sum of the images. Or in general, if you if you have a scalar multiple of a vector, then the image of that scalar multiple is the same of the scalar multiple of the image. So that's the property of a linear map. And you can immediately see this if the linear map is written as the A times X. So the other thing is that you could also interpret the coefficient matrix now, that the columns define the images of the unit vectors in the basis. So this is a more abstract notion of a matrix that is somehow here represented in this definition of a matrix norm. So you take now any unit vector. So if you take, say, the first unit vector and you do the matrix vector multiplication, you will have the first column of that matrix. Try to do that. That's a good exercise if you're still a little bit shaky on the matrix vector product. So take the first standard unit vector, 1, 0, 0, 0, and multiply the matrix times that first unit vector, and you get the first column of the matrix. Now, the matrix norm is defined as the largest vector that you can make by multiplying the matrix with the unit vector. So again, so the matrix norm is defined as the size of the largest vector you can make under this linear map. If that is abstract, think again of the first unit vector, 1, 0, 0, if you're in tree space. Then the multiplication of the matrix with that 1, 0, 0 is actually the first column of the matrix. So if your first column is kind of large, then actually also your matrix norm will be large. So matrix norms will indicate also the size of the matrix. So you can quantify what you mean by a large matrix. So if you do this with the 2 norm, we have what you call the spectral radius of the matrix. It's also the largest single value of the matrix and the largest eigenvalue A transpose A. So this definition leads us very deep into linear algebra. We will get to the singular value decomposition later in this course. But let me now indicate 2 other special cases. You can think of the column sum and the row sum. So the column sum is probably the easiest to understand, given that I just tried to explain that the columns of the matrix are the images of the unit vector. Are the images of the standard basis vectors. So you actually, with the maximum column sum, you actually look what does the matrix do to the standard basis vectors. So you have n very nice basis vectors. What does the matrix do to it? Other cases are then the Frobenius norm, which looks a little bit very similar to the Euclidean norm. So where you start squaring all the numbers in the matrix and you take the square root of this. Again, it depends. So these are 4 different norms. If your matrices are large, then they will correlate very well. Depending on the application that you work with, it may be that the spectral radius, the largest singular value of A, is actually easy to get, or that actually as part of your application, this is something that you want to compute, as we will see later. All right, what can you do with these norms? So for any norm, so again, we will leave off the P, the subscript. If our norm, if the property that we want to explain holds for any norm, for any P. So what are the properties? So if the norm is always a positive number, so it measures something, it's similar to the absolute value. And it's only when the matrix is identically 0 that you have a 0 norm. So one direction of the of this equivalence is obvious. If the matrix is 0, then also any norm will be 0. The other end is probably not that immediately clear, but let's not go in there. So the scalar multiple, if you multiply your matrix with a real number, then the norm will be multiplied with the absolute value. So the norm itself is not a linear map. So if you take the norm of the sum, you don't have the sum of the norms. However, the sum of the norms is actually upper bound. So that's called the triangle inequality. Also for the product of any 2 matrices. So now, again, be careful about the dimensions here. The second matrix here has to be in the sum of the same dimensions. For the product, the dimensions of the B need to match. So this is again catching up on the properties of matrix multiplication. So we will apply these properties in the matrix norms when it comes to estimating the errors on our linear systems. So we will compute a solution vector, and we will assume that we have the exact solution vector. Certainly we can do that if we have a test problem, and we will take the norm of the difference between the computed solution and the exact solution. That will be the measure of our error. So in a way, norms, they generalize absolute values. That's what we will use them for. So in Julia, norms are very easy to compute. They are provided within the LinearAlgebra module. So the norm by default is the 2 norm. So as you can see here, if you do not provide anything else than the matrix, you will get the 2 norm. Notice that we have the 1 norm, or we have the infinity norm. The infinity norm, which is the maximum of the rows, the 1 norm is the sum of the columns. And then also summed up, I'm sorry here. All right, so we will use that to, we will use norms to estimate how accurate our computed solutions are. And conditioning, again, is independent of any algorithm that we have used to solve it. So in a way, these condition numbers, they are independent of the algorithm. So they are a property of the problem. So this is a conceptual slide, which we have covered very early on in the course. And this picture we should actually keep in mind, as it describes the important quantities that we are interested in. So there is the forward error. So we have a space of inputs and outputs. We actually want to know the difference between the outcomes, so the exact outcome and the computed outcome. So we also essentially never work with exact arithmetic, but we have round-off errors. So the S bar is our solution map that is executed by a numerical algorithm. So we can also relate the other error is the backward error. So that's the difference between the inputs. And actually what we hope is that if the inputs change a little bit, the outputs will change at the same magnitude. So this is the conceptual slide with the forward and backward error. So we actually often do not have the exact input as well. So remember the 0.1, which is 1 over 10. So most of the time, we already make representation errors as soon as we enter numbers in the floating point format. All right, how does this now apply to the computation, to the checking of the errors of linear system solving? Well, as we have actually seen already last time, when we solve a system, we compute the residual. That's the norm of b minus a times x. If we have the exact x, then actually that will be 0. So the residual can be interpreted as what you need to add to the coefficient to the right-hand side vector to have your computed solution be the exact solution. And that's what this slide essentially presents. So if we are computing the residual, we don't know in general the exact solution. So we actually are working with the x bar. So we know from the fact that b equals a times x, we can replace b by a times x, and then we see that what is actually the residual that we computed, it is actually A times the forward error. So you see the relationship between the backward error, what we can compute, and the forward error, actually what we want to know. Now, what is in the way here? What is in the way is the matrix A. So, and you kind of see already now that the size of the matrix plays an important role. So if we have a matrix which has a small norm, because actually we will take norms of everything, when we have a small norm, our residual will actually be also the estimate for the forward error. And that's actually what the slide here tries to derive using the inequalities. So we have the first inequality on the residual, and we work with problems that can be solved. So the inverse of the matrix A exists, so we can derive the relationship between the residual and the forward error in two ways to get at a first bound. So we have that the forward error is bounded by above by the norm of the inverse of the matrix times the residual, and from below it is bounded by the residual again, but then now you have to divide by the norm of the matrix. That's a very first important relation. But actually we are often and mostly actually interested in relative errors. So the relative error is the absolute error divided by the size of the number that you're trying to compute. So we will derive the relative errors, but first let's do the same game that we played with the errors, the residual and the forward error. Let's do this also now on the B and the X. So the B and the X are also related by the A and the A inverse. So you can actually also already kind of predict the size of the solution. So with this inequality here, we can say that the norm of the solution is bounded from above by the norm of the right-hand side vector. So if you have already large numbers in your right-hand side vector, and you can see that, then you might expect large numbers in your solution. Not always, because there is also a lower bound. So either you divide by the norm of A or you multiply by the norm of A. Now, why are we doing this? Because we had the relative error here. So we divide by X. So actually that means that now we have two inequalities that we can start to combine. So we have just derived this important inequality. So that's an inequality on actually the inverse. So notice that when we invert X, we also have to invert the inequalities here. And we actually also write now the other inequality. So we derived on the previous slide this inequality. We reshuffle things a little bit so that the inequalities, they all go the same way. Okay. So here you see what will come now. We will actually multiply the three terms. Let's do this multiplication. And that actually gives us the important relationship on the relative error the relative error is here in the middle. So the relative error is bounded by the residual divided by the norm of the right-hand side vector. So what I just circled is what we can compute quite easily. We always compute, by the way, the residual when we have solved a linear system. That's always a check that we do. And computing the norm of the right-hand side vector is also a simple operation. Now the norm of A we could also compute. But now the inverse is actually now the unknown quantity, because if you are actually solving a linear system, you don't really know what is the inverse of the matrix. So in some sense, it's not exactly clear what this bound is actually really doing, what's the use of it. But we have a bound on the relative error. And we can formalize this. So let's see another way to see this bound is actually now looking into the other direction. So what is our input now? So in the picture with the two inputs and the outputs, actually what is sitting in the input at the left here is our matrix X and the right-hand side vector B. So actually we have a tuple. And what is the output is actually X. So you have the input space, which is our coefficient matrix and the right-hand side. And then we want to solve this linear system. So at the left, we have the inputs, at the right, we have the output. So that's the picture that comes with this. So actually, we are not solving the exact input. And then actually, we assume that all the errors on the input is actually on A. We assume that B is error-free. What we could always, and we can always achieve this by actually dividing by B. So the one, if we divide by, assuming now that we don't have zeros in the right-hand side, then we don't divide. But if the right-hand side is non-zero, we can actually divide out, and then we have exact numbers in the right-hand side vector. All right, so let's see, what we want to correlate is the error in the output with the error on the input. So now the picture, perhaps I will draw it a bit larger. So we have the input matrix and we have the output X. So we have the exact map that's going from the coefficient matrix, but actually we don't know the coefficient matrix exactly. So we have another error, which is a bar. So a bar is here, and here we have an X bar, so it's still very badly drawn. But I hope you kind of get the picture. So we have the forward error at the right, and we want to correlate this with the backward error. All right, so here is the derivation. We start from the exact relationships, and we gradually redefine. So the B can also be written as the modified. So the backward error actually indicates how much should you change the input so that you have the exact output. So actually what you have is that this actually satisfies. So you actually have satisfied the condition. And that is expressed over here. So we then write this out where we have the delta A. We isolate the error on the coefficient matrix. And we isolate this in this relation. Here we have the forward error, and here we have the error on the input. And that gets multiplied at the right with the x bar and at the left with the A inverse. And these relationships are all exact, provided, of course, that the inverse exists. So let's now take norms. All right, we are almost there. So we are having the relationship that we had on the previous slide. We take norms. So actually we apply the product property of norms times. So a vector is just a special matrix here. So provided that all the dimensions are correct, and there's no reason why they shouldn't be. So we have then the relations that the absolute error, absolute forward error, is actually bounded from above by these three quantities. So we can then divide by the norm of the computed solution to get the relative error on x, and then also the relative error on the coefficient matrix. So this gives us an upper bound, very useful upper bound already here. So we are, so see in the process, our errors will always be moderate. So it could be that you lose all precision, and then actually that condition may no longer hold. But if you have your numbers accurate, say to 4 or even 8 decimal places, then the vectors will in norm be not too different from each other. So you can actually replace the norm of the computed solution by the exact norm. That actually then gives you actually the relative error. All right, so this is an important relationship between, at the left, the forward error, and at the right, the backward error. Now, what is here at the right here is actually close to the machine precision. So you can interpret this number as the accuracy of the input. If you have measured your coefficients, say with 2 decimal places, then that is 10 to the power minus 2. And now we have this quantity that we already encountered, and that will be what we will call the condition number. So that's what this means here with the condition number. Why this is an important slide here. So I spent quite some time explaining how we got to this inequality. I do not expect that you can exactly reproduce everything, but what will be necessary is that you can use this inequality, that you can use this inequality to gauge the accuracy of a computed solution to a linear system. Here is it then. So the formula has 3 actors in it, and in some sense this is a definition here. So kappa, remember the kappa from the root finding problem. Here we also have a kappa of the linear system solving. So the relative error on the solution is bounded by the product of the condition number times the relative error on the input. And how should you be using this? So assume that the precision of your input coefficient matrix is equal to the machine precision, which is 10 to the power minus 16, but your condition number is 10 to the power 13. So how do you know this we'll get to that later, we will actually see that we can construct matrices with any condition number we like. Now then, independently of the method that you are using, for this example here, you can actually not expect to be more accurate than 3 decimal places. So the calculation is very easy. You add up the minus 16 and the 13 and you get to the negative 3. So that is a very simple calculation. And that's the first exercise. So the first exercise is formulated to resemble kind of an actual problem that you may encounter. You have a numerically computed solution, and your working precision was 64 decimal places. Now, what is the accuracy on the computed solution if you know a bound on the condition number of the matrix? So the reason for going into higher precision could have been that the condition number was 10 to the power 24. So if the condition number is 10 to the power 24, you actually can lose all accuracy in your solution. So it's can, so you can still be lucky. Okay. Now here with 64 decimal places, you can expect that you have 40. And it's the same calculus again. You do the minus 64, the error on the coefficient matrix, times the condition number. The magnitude is 24. Minus 64 plus 24 is minus 40. So you may expect 40 decimal places to be correct, but the justification, in your justification, you will have to write down the inequality of the previous slide. So you get half of points if you get the number right, and here it is 40, but you must also explain how you got to that number. That is the other half. All right, we talked about upper triangular matrices that were very nice matrices to work with. Well, here is kind of a shocking example. This is an example where the condition number rises exponentially. So in this exercise, you will compute the maximum column sum, and the inverse is already given. So from the last lecture, we could actually also have applied the algorithms to compute the inverse, but here I'm giving you the inverse. Exercise 3 generalizes this. So you can see the 4 in the example here is 2 to the power 2, and the 2 is 4 minus 2. And this is actually quite in general. So your given matrix has extremely nice numbers, but your inverse has very large numbers. Now, this is a pathological example. You may say, well, it's actually, we may explore this in a computational project. Random triangular matrices have very bad condition numbers, very bad expected condition numbers. So that's kind of a concern. All right. In the last 10 minutes, I will now see a more brighter side. So what are now the good problems? Well, random problems are actually good problems. I was actually a bit alarming that alarming you a little bit, that also random upper triangular matrices are no conditions. But random matrices in general are well conditioned. So here you see a 3 by 3 matrix, and the condition number is 8. So that explains that for very small matrices, random matrices, the double floating point precision is often gives you almost a full precision. What are the best condition matrices? Well, these are orthogonal matrices. In a linear algebra course, you may have seen the QR decomposition of a matrix. If not, then don't worry, we will get to the least square problem in another chapter, and we will actually see algorithms to compute the QR decomposition. Now, in Julia, in the linear algebra module, there is a QR function, and the QR function will actually give you the orthogonal, what is called an orthogonal matrix, and will be a way to reduce. So here you see what it means to be an orthogonal matrix. So you can interpret now the matrix Q. In the columns are vectors, so these are three-dimensional vectors, and they are perpendicular to each other. So if you multiply the vector with itself, you get 1, 0, 0 back. So that says that the length of the columns is actually 1. And if you multiply, so the off-diagonal numbers are actually the products with the other vectors, with other columns in the matrix. So the condition number is perfect. How can you explain this otherwise? You can perhaps let me skip first to the picture here. So when you have to solve a linear system, what you actually are doing geometrically, you are intersecting, at least in the plane, you are intersecting lines. And you can expect that if the lines are perpendicular to each other, then it's very easy to see the crossing. Now, if they start to cross each other in a more, if they come much more closer to each other, then actually you can see that it could get harder and harder to solve it. So in a way, you could also now view conditioning geometrically, at least in the plane. So you start at the left with an orthogonal or an orthogonal problem, and you kind of pull these two lines more and more closer to each other. At the point when they either are parallel or fall on each other, then the problem is no longer well defined. So you have an entire spectrum of well-behaved problems, excellently behaved problems, and very bad problems. How can we use this? Well, we know that we can make random matrices of a prescribed condition number. So here we can start with actually the nicest identity matrix. So if you ever had to solve a linear system, and the nicest coefficient matrix is actually the identity matrix. But you can actually make it bad by making the last or one of the elements on the diagonal very tiny. So this is here 10 to the power minus 8. So we go from a condition number that is 1 to a condition number that is 10 to the 8. Another way to see this geometrically is that if you would have made the last diagonal element 0, you would have gotten a matrix that is called singular, so with a 0 determinant. So the 10 to the power minus 8 is kind of the distance to the nearest singular matrix. That's also how you can interpret the condition number, again as an estimate of the distance to the nearest singular matrix. And that measures the difficulty of the problem. Now, if you have to solve a problem like that, you will very quickly change it into a scaling problem. So these three linear equations will be decoupled. And that means that it then simply can be rescaled. Now, with random matrices, you can no longer do this decoupling. You no longer have this decoupling. And that's actually getting very close to the last exercise now. You can actually make matrices, and as you can see here, the matrix B is a matrix. Well, there are some small numbers in there, but they're actually not that small. So in a way, it's kind of a matrix. It's a 3 by 3 matrix, and the smallest numbers are kind of 10 to the power minus 2. So you wouldn't actually expect that to be a difficult problem, but it is. So here is the recipe for cooking up matrices like this. We take a random matrix and we compute its QR decomposition. So Q has a very nice condition number, but we multiply this with the identity matrix where we have put in a very tiny number. So here I took again the minus 8 because I wanted to have a condition number that is 10 to the power 8. But if you wanted 10 to the power 64, well, you could have accomplished that with 10 to the power minus 64, although then your working precision might have also have been that large. So here, I think the experiment should be always within the bounds of the machine precision, I should say. Okay, but the punchline is that you can make, and we can make, any matrix that actually looks not too suspicious. So looking at these numbers, we wouldn't really expect that we will most likely lose 8 decimal places when we try to solve this problem numerically. Because B is actually very close to a singular matrix. So any representation error on the matrix B will actually almost make it very close to the singular matrix. Oh, now I have last 2 minutes to explain the exercise. So here you see what now happens. So if you have to solve a linear system within Julia, please use the backslash operator. That's the quickest way to do it. We will see algorithms to solve linear systems, but the backslash is quite good. Here I generated a random matrix, and because I want you to redo this experiment, I fixed the seed. So the matrix that you get from the random number generator will always be different if you don't fix the seed. But here you should always see the same results, which means actually the same errors. So how will you explain the error of the last computation? You will compute the condition number of A, and you can actually explain it also here, without actually computing it, but please, so there is the cont command, so you will compute the condition number, and then go back to the reasoning of the first exercise. Because the condition number is 10 to the power minus 8, the error on the solution, so we were expecting to see exactly 1, but the error is actually 10 to the power minus 8. And the 10 to the power minus 8 comes from the minus 16 plus 8, from that equality from the first exercise. My 50 minutes are up, so I will stop here.